So, welcome back to my study guides channel, and this guide was supposed to be sent well finished by yesterday, but I forgot. So it's 9:30 in the evening, and I also gave myself the challenge to fit everything in one canvas so that we don't have to deal with those annoying cuts. So welcome back to my channel. This is going to be for the upcoming science test. It's all about carbon compounds, and the mole concept, as well as the percentage composition of a compound. So let's start. I've made a graphic organizer here, and as you can see, we'll just focus more on organic. So we start with the carbon atom. Its atomic number is 6, and it has 4 valence electrons. It is found over here in this periodic table, as you can see, and it has an atomic mass of 12.01. So we don't really need to memorize these because these are always given. Now, once you have a carbon atom, carbon atoms can form numerous amount of compounds, and they can be classified into a lot. But we're only gonna focus on two, which is the organic here and the inorganic here. Remember that if anything is just made out of carbon purely, such as graphite and diamonds, those fall under inorganic because they just are kind of purely made out of carbon and no hydrogen bonds are present. But an organic compound would fall into one of these four categories, which have a carbon-hydrogen bond somewhere. And as you can see, there's quite a lot of subcategories. So I'm going to be explaining each one. So first and foremost, for hydrocarbons, these are single bonded carbohydrons, so C and H. So when you draw this as a diagram, if you see one of these diagrams, you really need to just look out for these lines over here. If they're all made out of single lines, as you can see, they're all single lines. I'm highlighting there. That means it's a what do you call this? It's a hydrocarbon, and it falls under alkanes, as in alkanes. Now it also has the the chemical composition similar to this, where N is equal to the amount of carbon, or N can be any number as long as it follows this value. For example, if we have three carbons, that means we have 3 times 2 plus 2 hydrogens, which is just 8, because 3 3 is the N, then times it by 2 is 6, then we get a plus 2, it's 8. You do have to memorize these formulas over here as per the the formative test I took. It does require us to know which one is which. So there's a pretty neat trick here. And alkanes always end with ANE. So ANE. So for example, butane over here ends with an ANE. So this is mostly used in fuels, as we can see over here, as well as gasoline. So in conclusion, for alkanes, it's a single bonded with this formula, and it's used in fuels. It looks like this. By the way, I forgot to add, but this is the one that is saturated. Okay, next one. Alkenes, as in E. Alkenes. This one, unlike our previous hydrocarbon alkanes, has this time at least one double bounded carbon and hydrogen. And to visually see this, we have to look at this one here, the drawing I made here. As you could see, I told you to pay attention to the lines over here, and this time there's a double line over here indicating a double bond. When drawing symbols like this, make sure to also follow the octet rule. You don't really have to notice it here because you can just surround it, because there's like 1, 2, 3, 4. That's 4. And then carbon has 4 valence electrons already, so that makes 8, which follows the octet rule. However, what about here? So we have 2 over here, that's counted as 2, and then we got 3 and 4. We don't need to add another H up here because we already have 4 valence electrons to add to the 4 existing ones, which makes it 8. So therefore, this is how we draw a alkene if we're asked to do so. These are used in rubber and plastic. So we have the chemical, or not really chemical formula, but what do you call this? Composition formula of for every carbon N, there's hydrogen of 2N, which means there's just double the amount of hydrogen as there is in carbon. So if C is equal to 5, so there's 5 carbons, that means there's simply 5 times 2 carbons. So that hydrogens. So that's 10 hydrogens we have over here. So it's very simple. Remember this formula for alkenes. And just like alkanes, alkenes end with the E and E. Next is alkynes, and I hope by looking at the preview you can already start to get what's going on here. So unlike the previous two, this one has at least one triple bond of C and H, and it's mostly used in preservatives. The chemical formula for this is for every Cn, it's H 2N minus 2. By the way, these two are both unsaturated. I'll explain later. So these two are both unsaturated. So once again, alkenes are used in preservatives and have this CH formula. So let's use 5 again as our example. So we got C is to 5, then we got 5 times 2, which is just 10, minus 2, which is just 8. So therefore, it's just 5 and 8 if you have an alkyne with 5 carbons. Once again, following the octet rule, we got 3 valence electrons here, and now we have 4. Therefore, this is already stable because we have 1 over here, 3 over here. That makes 4 additional valence electrons. Then we got carbon itself, which already has 4, which makes 8. Therefore, the octet rule is passed. Lastly, for aromatic, it's just the presence of a benzyne ring. If you see some hexagonal shape over here, that's basically what we call an aromatic. It's just used in primarily medicines. And that concludes our section for hydrocarbons. Meanwhile, for alcohols, they have an OH attached to carbon, and they're usually just used in drinks and medicines, and similarly like how all the alkanes, alkenes, and alkynes follow this prefix over here, it ends with OL this time. So it looks something like this, and you can attach any element over here, over here, over here, over here. You can just add anything as long as it has this base structure that's considered an alcohol. There's no formula because it's very, it's free. It's free. It can be any element. So there's no formula you need to master here. Same thing here with esters, which have a presence of COOH. And once again, with the letters R, it has, what do you call this? It can be any element. You can put any element here as long as it follows this basic structure. These are volatile, but are responsible for the sweet smells and even the aroma of some fruits. Lastly, we got biomolecules, and honestly, this is where I start to struggle a bit. We don't need to memorize which of these are which elements are comprised, but we need to know the differences between all of them. So you can basically just ignore this. These are just in case you need to know, so you can ignore these. Carbohydrates. These are just the main source of energy and are found in cells. So this is where we get our food from, and that's where how the mitochondria is powered. Mitochondria, sorry. I forgot. But it's just the main source of energy. And when your body needs energy, it goes to carbohydrates. Meanwhile, for lipids, on the other hand, they're very, very, very similar to carbohydrates. They're both comprised of the same elements, CHO, and they're both sources of energy, but this one is long-term energy. So the reason why lipids or fats are long-term energy is because once you start to not eat for a few days, your body starts burning these lipids or fats. It uses its fats as its energy source. So that's why it's called long-term energy storage. But the startling difference here is the non-polarity of lipids or fats once again. Just like oil. Oil is not soluble in water. It's a non-polar one. So that's what distinguishes carbohydrates from lipids. Sure, they're both sources of energy. Sure, they're both made out of CH and O, but lipids are most certainly non-polar. Meanwhile, for proteins, this is muscles and your nails, and are basically made of carbon, hydrogen, oxygen, and nitrogen. It supports the immune system, and that's all you need to know. Lastly, for nucleic acids, it's comprised of carbon, hydrogen, oxygen, nitrogen, and phosphorus. Phosphorus. It synthesizes the proteins in cells and it carries genes. So remember, DNA, this goes under nucleic acid. So that's all for it actually. We've ticked off the entire first unit in about, let me check, in about 10 minutes. Yeah, 10 minutes. That's the carbon atom, that's organic compounds and their uses, and we definitely talk about biomolecules. There you go. One shot, one kill. Next is the mole concept. Now for parts 2 and 3, you don't really need to define what a mole is, but I will define it anyway. So a mole is basically follows this number made by Avogadro. Avogadro's number is 6.02 times 10 raised to 23. A mole is a fixed unit where the amount of grams is equal. We're gonna calculate the molar mass in this formula, grams per mole. Basically, let's say 5 grams of a substance. When you put 5 grams per mole, it means to achieve Avogadro's number, mole, you need 5 grams of this to achieve this amount of particles. I'll show you a visual example of that later. Meanwhile, molar mass is the one that we have in compounds over here, like this one over here. We just need to find the individual atomic mass of this one. See, we have to find the atomic mass of, let's say, potassium, sulfur, and oxygen. Then we're gonna add it all up, and that will be our molar mass. It's basically the sum of the atomic masses, the atomic masses in a compound. So with that out of the way, that's really all we need to know. Most of these are just formulas. We'll be using all 4. There's one I forgot to mention here, but you'll see in a bit. First one, a chromium, a transition metal, is component of chrome plating. Chrome plating is used on metals and steel as to control corrosion. Calculate the mass in grams of 0.045 moles of chromium, and we need to round off to do decimal places. First, it's asking us to convert a mole, as you could see, to mass. Let's go back here. Mole to mass. So we need to focus on this one over here. So we need to ask ourselves, is chromium an element or a compound? In this case, it's an element. Therefore, a mass of the element is equal to the number of moles times the atomic mass. So we are given an moles over here. That's 0.0450, I guess, times, let's see, we need to find the atomic mass of chromium. So Cr is over here, which means it's 52.00. 52.00. So, don't worry, you can use calculator on the test. So let's type in our calculators together. 0.0450 times 52. We get an answer of 2.34. And 2.34 grams. It's just going to be grams for this one because we're not converting anything. We're not converting anything yet. Because this is just This is just an element, and it doesn't need it. So therefore, we have 2.34 grams of chromium in 0.45 moles. So we can box out our answer. Alright, this is where we have to calculate the molar mass first. we have to find how much mass of 2.8 calcium chloride. 2.8 moles of calcium chloride, sorry. So to calculate the molar mass, we first need to determine the components in calcium chloride. So as you could see, we most definitely have calcium. And then we need to look at the subscripts to see how many are there. As you can see, there's only one calcium. So calcium times 1. And then we also have chlorine, which we also have 2 of. Cl times 2. Now, we just need to find the values of calcium and chloride respectively. The atomic masses first. So Ca over here has an atomic mass of 40.08. So since we're just looking for 1, it's going to be 40.08. Meanwhile, for chlorine, we have Cl over here. That's 35.45. 35.45. And since we have 2 of them, we have to add times 2. So, we have 35.45 times 2. That's equal to 70.9. And then we just plus these together. So 40.08 plus 70.9 is equal to, let's type that in our calculator. That's equal to 110.98 grams per mole. But we aren't supposed to find the molar mass. We need to find the, we need to multiply it by 2.8 because we don't want 1 mole, we want 2.8 moles. So as you can see over here, we just followed that. We just found the molar mass first, and then we found the number of moles by the given. So we need to do this times 2.8, which is equal to 310.744, but we only consider up to 2 decimal places, so it's just 310.74 grams. Hope you're getting it so far, because most of the test answers are like this. Oh, by the way, before I move on, to find molar masses with like this, like if there's a bonded like H2O over here, like 6H2O, let's say, you're just gonna have to add these together. So like find the molar mass of this one first, and then you have to find the molar mass of 6H2O. So just find H2O first, and then multiply it by 6. Anyway, we've now converted from moles to mass. Let's do mass to moles. So sample problem number 3. We want to find how much moles of gold is present in 10.2 grams of gold. Remember to round off to 2 decimal places. First and foremost, we are given that 10.02 grams of gold. Gold is definitely an element, so gold is an element, so we need to put mass to mole. So for given, this is it. So mass of element is 10.2 grams. Then we need to find the atomic mass, which is a fixed value. So you need to find AU, which is here, which is 196.97. So you do 10.2 divided by 196.997. That's equal to 0.051, or that's just gonna round off to 0.05 moles. Last one. How many moles of water, H2O, are present in 250 grams of ice? So we need to find the molar mass first of H2O. So H2O, we got H, 2, and O. And looking at the periodic table here, we got H at 1.01. So we have H times 2, because we have H2 is equal to, that's equal to 2.02, because 1H is 1.01. So it's just 1.01 times 2. And then we can just copy oxygen, which is equal to 16. Over here, oxygen. Then we just add it up to get 18.02 grams per mole. Now we have the molar mass. We're going to apply this formula over here. The number of moles is equal to the mass of compound over molar mass. So the mass of compound that is given to us is 250. And the molar mass we calculated for is 18.02. Therefore, plug it into the calculator. We give us 250 divided by 18.02. That's equal to 13.873. Or rounding off, just 13.87 moles. And there we go. That's unit 2 down. Pretty fast, and I hope you're getting the gist of it. I will feel free to ask me any questions in the comments. Just comment the timestamp. Last one, and this is just the same thing, but now we have to add an additional step. So, seaweed farmers in Barangay Santa Rosa want to find to boost their yield using potassium fertilizer, but are unsure whether to use potassium chloride, KCl, or potassium sulfate, K2SO4. So, we need to find the one that has a higher percentage of potassium, which is K. So how do we do that? Let's consider both of our options here. We got a KCl and a K2SO4. What we're gonna have to do is apply what we learned from the last time, which is calculating the molar mass. So, let's start. First and foremost, to find the molar mass, we need to take a look at each element. First, we got K, potassium. Over here, we have 39. We have 39.10. K equals 39.10. And then Cl, chlorine, we have 35.45. And since we don't have any numerical coefficients, we can just go to the molar mass straight away, which is equal to, let's type that in our calculators, 39.10 plus 35.45, that's equal to 74.55. Now, to find the percentage formula of a given element in a compound, we just put element mass over molar mass times 100. So let's plug that in. We want to find the more potassium fertilizer. We want to have the more potassium. So we only have to focus on K over here. So we have the element's mass or element's contribution to this one, which is 39.10 over the molar mass, which is 74.55. And then we have to times that by 100. Let's put that in our calculators. We get 39.10 divided by 74.55 first. Then we times that by 100. And that's equal to 52.448. Or, since we have an 8 over here, we need to round off to 52.449%. 449, not 449. Sorry about that, guys. Let's just make sure. I'm gonna check the notes I had. Sorry, yeah. It's 45, sorry. I'm so sorry. It's 45. Sorry, it's 45 because 48. So therefore, we just have to round this to 45. I'm so sorry about that. Anyway, we have 52.45%. So let's move on to the next one. So let's count our elements. We have K. Let's do the same thing again. So we have K. K, S, and O. Potassium, sulfur, and oxygen. So we got K times 2. We have 2 sulfurs, 2 potassiums, only 1 sulfur, and 4 oxygens. As you can see over here, 2 potassium, 1 sulfur, and 4 oxygens. Now we need to find the mass for both, the atomic mass for all. So we know that from previous example, we have potassium is 39.10. And then we have sulfur over here, that's 32.07. So add the times 2 there. Then we got an O times 4, which is just 16 over there. Times 4. Let's first multiply these over here. So 39.10 times 2, that's equal to 78.20. Copy and paste the 32.07. And we got 16 times 4. That's just 64. Then we need to add the 78.20 plus 32.07 plus 64. That's equal to 174.27. That's your molar mass right there. So once again, we need to put this formula into account. So we need to find the element's mass or contribution to it. So that's potassium. And it's going to be 78.20 because we have 2 of them instead of 1. Then we just put that over the molar mass of 174.27. Then we times that by 100. Let's plug that into our calculator. 78.20 divided by 174.27 is equal to this one, and then we have to times it by 100. So after timesing it by 100, we get 44.872, or simply just 44.87%. And that's our final answer. We just need to check which one has more, the bigger value. Therefore, the answer is KCl. And as you can see over here, that is, believe it or not, that is the entire test basically done in just a single page and a single breath as well. Not really a breath, but a single recording. Whew, that's pretty tiring. This is probably one of the shortest, the least amount of time I spent on a study guide. But yeah, once again, I do sincerely apologize. I was just so tired after this week. I completely forgot I was supposed to do this. So once again, please accept my apology. I truly apologize for the inconvenience of setting up, of uploading this late. But I wish you all the best and make sure to take care of yourselves. See you next time, and yeah, bye. Thanks for watching. Oh wait, yeah, I forgot to do this. There we go, we're complete now. Thanks for watching again, sorry about that.